All right, here we are at Newton's third law. Action and reaction. This one's actually pretty easy, and you've probably heard most of this before. According to Newton, whenever objects A and B interact with each other, they exert forces upon each other. So whenever two things touch or have the field force, both of them affect each other. When you sit in your chair, your body exerts a downward force on the chair, and the chair exerts an upward force on your body. There are two forces resulting from this interaction, a force on the chair and a force on your body. These two forces are called action and reaction forces, sometimes known as action-reaction pairs, and are subject to Newton's third law of motion. This is what Newton's third law is all about, your action-reaction pairs. So, formally stated, Newton's third law is this: for every action, there is an equal and opposite reaction. I'm sure we've all heard that before. Basically, you can't touch without being touched. That's Newton's third law. So, forces will always come in pairs, equal and opposite action-reaction force pairs. So, you'll have one action and another action. One is going to be the action, one's going to be the reaction. And it doesn't matter which force you call the action or reaction because they both happen simultaneously. So it does not matter which force is first or second. They both coexist. They are equal in strength and opposite in direction. All right, identifying action-reaction pairs. Consider the interaction between a baseball bat and a baseball. So we have them hitting each other. The ball hits the bat, and the bat also hits the ball. So, the baseball forces the bat to the right, an action, and the bat forces the baseball to the left, the reaction. Or I could have switched it around, it doesn't matter. Alright, consider the following three examples. The action force is stated, determine the reaction force. An athlete pushes a bar upwards. So our action is the athlete pushes the bar upwards. What's our reaction? So what's pushing downward? If the athlete is pushing up, the bar pushes down. That would be our reaction. So now we have a bowling ball pushing to the right. What would it be our reaction? The pin pushing to the left, back on the ball. Compressed air pushes a balloon outward. So the air is going this way, but the balloon is going to go that way. So let's take this a little bit further and figure out some more of these. So, a gun recoils when it is fired. The recoil is the result of an action-reaction force pairs. As the gases from the gunpowder explode and expand, the gun pushes the bullet forward, and the bullet pushes the gun backwards. The acceleration of the recoiling gun is greater than the acceleration of the bullet, smaller than the acceleration of the bullet, the same size as the acceleration of the bullet. The answer is B. The force on the gun equals the force on the bullet. However, the acceleration depends on both force and mass. The bullet has a greater acceleration due to the fact it has a smaller mass. Remember, acceleration is inversely proportional to the mass. Alright, rockets are unable to accelerate in space because these are kind of messed up. There is no air in space for the rockets to push off of. B, there's no gravity in space. C, there's no air resistance in space. D, nonsense, rockets do accelerate in space. The answer is D, rockets accelerate in space by burning fuel and pushing the exhaust in the opposite direction in which they travel. So if you have a rocket that is burning fuel and it pushes the gas out this way, which way does the rocket go? The rocket will travel that way. Imagine a place in the cosmos far from all gravitational and frictional influences. Suppose an astronaut in that place throws a rock. The rock will A, gradually stop, B, continue in motion in the same direction at constant speed. The answer is B. According to Newton's first law, an object will continue in a motion at the same speed and direction. Because if you throw it, let's say at 5 meters per second, and there's no gravity or anything to act on it, it's going to continue moving at 5 meters per second. There's no resistance or anything to it. So it's going to continue on following Newton's first law. A 2 kilogram object is moving horizontally with a speed of 4 meters per second. How much net force is required to keep the object moving with the same speed in the same direction? So we have a mass of 2 kilograms moving with a speed, so V, of 4 meters per second. How much net force is required to keep the object moving in the same direction? The answer is 0. An object in motion will remain in motion in its state of motion. Newton's first law. The presence of an unbalanced force would change the velocity of the object. So if you're going to change the velocity, then you would put a force in. But if we want to maintain the same, you don't need it. If you were in a weightless environment in space, would it require a force to set an object in motion? Yes, absolutely. Even in space, objects have mass, and if they have mass, then they have inertia. Inertia is an important concept. Inertia is the reluctance of an object to change its state of motion. The reluctance of an object to change its state of motion. It's also, Newton's first law is sometimes called the law of inertia, because basically the inertia says if it's standing still, inertia says it wants to keep standing still unless a force comes and moves it. Or the inertia says if it's moving at a constant speed, its inertia says it's going to keep moving at a constant speed unless an outside force makes it move. So that is an object in space resists its change in motion. A force must be applied to set a stationary object in motion. That's anywhere in the world. You have to, if something's at rest, you have to apply a force to it to get it to start moving. Newton's laws are everywhere. Mr. Newton spends most Sunday afternoons at rest on the sofa, so he's a couch potato, watching pro football games and consuming large quantities of food. What effect, if any, does this practice have upon his inertia? What's this going to do with his inertia? Well, Mr. Newton's inertia will increase because he keeps eating and eating large quantities of food. Mr. Newton's mass will increase if he makes a habit of this, and if his mass increases, then his inertia also increases. So if mass goes up, inertia goes up. If mass goes down, inertia goes down. If the forces acting upon an object are balanced, then the object must not be moving, must be moving with a constant velocity, must not be accelerating, or none of these. The answer is C. Could be A, but it doesn't have to be A, and it could be B, but it doesn't have to be B. An object having balanced forces definitely cannot be accelerating. This means that it could be at rest and staying at rest, or it could be in motion at a constant velocity, but either way, it is not accelerating. Does a person diet to lose mass or to lose weight? Explain. Generally, people diet because they wish to reduce the amount of matter on their body. So people diet to lose mass. If one wishes to lose weight, they could get a six-fold reduction by moving to the moon. So if you go to the moon, you're going to weigh less, but your mass is still going to be the same. And here's just a few little cartoons to brighten your day. Here's another one. I actually have a friend of mine who is a pediatrician. She is a very smart person. And every time I tell her that I'm still teaching physics, she goes, "Physics is magic." And she went to A&M, and on one of her physics tests in college, she wrote down as an answer, "Physics is magic." And yet another funny little haha. All right, that's the end of Newton's third law, and we will do problems in class.